the capacity or the maximal capacity of any cart defines the maximum flow. Okay. Sorry, the minimum capacity. The minimum capacity of any cart defines the max flow. The issue is how do you find such a minimum capacity? Okay. So I will first go over the three proofs. Okay, three not exactly kind of. It's we have these three statements. Okay, they are equivalent. So once we finish the proof of these equivalent statements, okay, the way to find them, the minimum capacity of any cart will become obvious. Okay. So first, okay, there exists a cart whose capacity equals the value of F. Okay, for some flow F. Okay, so that cart, there's a cart whose capacity equals to the value of the flow. And we know the capacity of a cart, it should be greater or equal to the flow, right? So when the capacity equal to the flow, F, that means, okay, well, from 1 to 2, F is the maximum flow. Obvious. Why? Because you wouldn't be able to find additional flow to it, because otherwise, as I said, it's going to be over that capacity, right? Supposedly, the basic idea. Okay, let me prove it. Okay, when we say a cart, for example, a cart like this, when you have an augmentation path, okay, that augmentation path must go through some edge, okay, in between this, through this cart, right? Because for a cart, one side is set A, the other side is set B. So, and the set A contains source node S. Set B contains the sink T. So if you have an augmentation path, that augmentation path must somehow go through this cart. In other words, it must contain one edge in between these two carts, right? So you can see that, for example, in this cart, okay, we have pretty much 4 different edges, right? This one, this one, this one, and this one, right? We have 4 different edges. So your augmentation path must contain at least one of such edges, right? In order to go from S to T. Because this cart pretty much break the graph into two different sets. To go from source node to sink node, you have to go through one of those edges. So when I say the minimum capacity of any cart, okay, what I'm really talking about is, again, the bottleneck. Yeah, previously, the critical age, I was using the bottleneck. So here, it will be very, very convenient to use this term again. Okay, 就是我还是可以用那个就是那个瓶颈，在这个 cut 里面 in any cut, okay, that capacity pretty much define like the maximum flow, because once you use up all the capacity in this cut, I mean, you don't have additional augmentation paths that can go through this cut, right? So that's the basic idea. But anyway, so there exists a cup whose capacity equal to the value of F. I mean, as I said, like for any cup, the capacity of the cup will be greater or equal to the flow. Okay, F. So when the capacity equal to the flow, that means F must be maximum, because it is impossible to increase the F, because like adding additional F it's going to violate, it's going to exceed the capacity of that cup, which is impossible. Okay, so F, the second one, from F is the maximum cup, the second one to the third one. Okay, there is no augmenting path with respect to F. So if F is the maximum flow, okay, there must not be any augmenting path. Okay, why? Because if you could find augmentation path from source to the sink, that means you are able to add additional capacity to your flow F. Then the flow F is no longer maximum flow, right? So this is done by contradiction. If there were augmenting path, okay, then you are able to add additional capacity to your flow F. Then F wouldn't be maximum flow. So, well, it violated the assumption. So, yeah, so this is like, you can go from 2 to 3. And from 3 to 1, there's no augmenting path with respect to F. Okay. How do we say it? There exists a cup whose capacity equals to the value of F. It's like this. If there's no augmenting path, what does that mean? I mean, you do, let's say we do a breakfast search. We do a breakfast. I mean, we can do either like breakfast search, the Ford Robinson or like the Edmunds car. Doesn't matter. Anyway, let's assume that we do breakfast search. So from source, we try to go out. We try to reach out, I mean, to any node by using the, I mean, here we are considering the residual graph. Okay, so after we assign, the flows, we assign all the flows. Okay, so this is source. This is sink. Okay, so you can use either depth first search or breadth first search, okay, to traverse, to try to reach out to all the nodes you can possibly reach, okay, with like a remaining capacity. If there's still capacity left, then you can, for example, you can go from S to some nodes. So we have some nodes here. Of course, the worst case scenario is, you just don't have any edge that you can take advantage of. If that's the case, well, this left side contains only one node, node S. ，right？ 就是你现在就是从 S， 你考虑那个剩下的 capacity， 那你用那个看你要 depth first search、reference doesn't matter， 你就是想办法去 reach 所有你可以走到的节点 ，OK？ 那当然我们假设说那个还有一些 capacity 留下来，你这样走，就你从 S 可以 reach 到所有的节点，你叫这个 ，you call this set A。 And you call the remaining nodes, which obviously contain like a sink. You call this set B. And because there's no augmenting path, right? You must not able to reach from source to sink, right? By doing so. If you're able to reach from source to the sink, by either depth first search or breadth first search, using the residual graph, something's wrong. That means that means there is augmenting path available, right? Which is here. Remember, we are assuming 3, we want to prove 1. So 3 tells us there's no augmenting path available now, right? So if you try to go from S, okay, somewhere you must, you cannot reach T. If you can reach T, you have augmenting path. Then this statement 3 is not valid. But that's our assumption, right? Okay. So anyway, the nodes that can be reached from the source S, we call this set A. The rest of the nodes we call the set B. And then, okay, you consider the path here. Okay, because you can no longer reach, you can no longer extend to reach here, right? So because it means all these edges, you have used all the capacity, right? You have used all the capacities. So in other words, their capacity will add up, will equal to the total flow, right? If there's still capacity left, you can take advantage of that, right? But if you cannot, that means that you already used all the capacity. So that kind of force your capacity to be equal to be the same as the total amount of flow received at the node T. Okay? So this is going to be, the cart whose capacity equals the value of F. Okay? Is it okay? So this actually gives us an algorithm to find the bottleneck. Okay, this actually gives us an algorithm to find the bottleneck. Of course, first you need to push the maximum flow, right? Once you have the maximum flow, okay, once you have the maximum flow, and then starting from S, again, use a reference search, whatever, okay, you find the reachable nodes and the rest of the nodes, the edge between the boundaries will be, like your bottleneck, or it will be the minimum cut, okay, Okay. So you use Ford Focusrite or like Edmonds car and whatever to determine maximum flow first. And then, it takes like, some time, but depends on what algorithm you use, obviously, right? So, Ford Focusrite is a little bit slow because you can see that the time complex is N times F, where F stands for like the size of the maximum flow. That is something that we don't like. But anyway, okay, let's assume we use the Ford Focusrite. And then we try to, start from S, we try to use either like breadth first search or depth first search again, okay, to reach out. So again, like it's like it's another depth first search and breadth first search. It's E plus B, and V is small, so basically it's E is N here. So it's going to be NF, BO, NF, which is like assuming we are using for composite plus BO, N. So this is like the amount of time, okay, to find the mean cut, max flow mean cut. Okay. Of course, if you use Edmonds cut, the complexity is going to be different. Okay, it's going to be VE squared, right? VE squared plus VE squared EV squared. Yeah, I think like VE squared, VE squared, VE squared, VE squared plus like E. Okay, so it's still VE squared. Depending on what algorithm you use in the first step to find the maximum flow. Okay, and that's like the up where like the up and down for the complexity. Okay, so we are down here. So. I'm thinking about like using a different slide for like P and NG, but this is like something like okay. If we use this one, I will give you this slide. I will upload this slide. So I have a slide for like a complete, right? In the E class, right? So this one is a slightly different because this one cover a little bit more challenging problems. So I think I will use this one. Okay. So obviously we don't have enough time to finish this. Today, but next week we should have like we should be able to finish this one like earlier. But we don't have time to talk about more material, and I think it should be appropriate to start in this chapter. Okay, start at this chapter. Okay. So anyway, so far. You have seen different algorithms, okay, for different problems. So you see running time can be like big O n squared, big O n squared, big O n log n, big O n, and so on. So there are all sorts like of time complexity for different algorithms. So for all these algorithms, we call them polynomial in terms of the input size. So this n symbol stands for the input size. Okay, they stand for the input size. Some of them may stand for like, because when you see like more than one variable, that means like you have like more than one variable for the input size. For example, like we just talked about like Edmund's car, like it's as I say, it's VE squared. Okay, I mean V is a number of vertices, E stands for number of edges, but basically like that's like both of them define like the size of the problem. Yeah. So can we solve all the interesting problems in polynomial time? We hope that. Okay, we are in computer science. We hope we can do that, but unfortunately, it's not that easy. It's not that simple. Okay. For example, this is one question. Okay, given an arbitrary graph. Okay, this problem is called traveling salesman problem, or abbreviated as a TSP. So the input is an undirected graph with weights on each edge. Okay, and the output, we want the output to be like the shortest tool that visits each vertex exactly once. Okay, the basic idea is, well, you are a salesman, and each node represents a city, and the edges between the nodes represent, for example, the highway or the path between cities, and the weight associated with each edge represent for example, traveling time. For I mean, when you take the route, okay, of that, I mean, represented by that edge. Okay, so when you want to minimize, okay, you find the shortest tool. That means you minimize the amount of time you spend, okay, for your job, right? Because you are a salesman. And what is your job? You are a salesman, so you have to visit every city, right? You have to visit every city. And to optimize it, so we only want each city to be visited at most once. So that's what we call traveling salesman problem. Okay. So this is what we call optimization problem. Okay. Because we are not asking, the answer is not yes or no. The answer is the shortest path, right? So it's an optimization problem. Okay, it's not just a yes or no question. So the best known algorithm is big O n times 2 to the power of n time. So this is pretty bad, right? Because so far all the algorithms we have discussed, throughout the whole semester, I mean, it's not polynomial, right? If an algorithm is polynomial, we consider it's very, very bad because it doesn't scale. Okay, when the problem size increases, the time goes up so fast, so we don't like it. Okay, so traveling salesman problem is one of such problems that is difficult. Okay, I probably should say, so far nobody can solve it in polynomial time. Okay, so here we have another problem. Okay, we also consider this problem difficult. Okay, we call it click. Okay, click is also about the graph. Okay, so the input is just an undirected graph. Okay, and the age even does not have weight. Okay, the previous one, the traveling salesman problem, each age is associated with the weight. Here, we don't even have weight for the age. Okay, it's just an umbrella graph. I mean, where the age just connect like two nodes. That's it. Okay. So, what is the output we are looking for? We want the largest subset of nodes. Okay, from all the nodes being proposed. Okay, such that every pair of vertices in this subset has an age between them. Okay. So in the graph, I mean, you know, like such thing is called like a complete graph, right? If like I mean, every pair of vertices have an age between them. I mean, we call such a graph a complete graph. So yes, we are looking at a subgraph that is a complete graph. Yeah. So a complete subgraph is called a clique. Okay, that's a special terminology used in like graph theory. Okay, for this problem, okay, the best known algorithm is also big O n times 2 to the power n. In other words, it's also exponential. So it's also very bad. So we have, well, it is not necessary the difficult problems are graph problems only. There are other problems that are not about graph, but they are equally difficult. Well, probably I can say, at least as difficult as those problems I'm previous. Okay, so what can we do? So remember what I just said. I was saying that these problems, so far, nobody can design a polynomial time algorithm. So take a closer look at what I say. I said the best known algorithm is like that. The best known algorithm. Okay. I mean, you may be smart, right? You may be like the smartest guy in the world. So you can design an algorithm that beats the best known algorithm. Okay. So that your algorithm is polynomial. Is it possible? It could be. Like, who knows, right? Who knows? The issue is like this. Okay. So you have choices. Okay, it sounds like I'm talking about matrix, but anyway, no. So the first option is you spend more time designing algorithms for those difficult problems. Okay, so obviously there are many smart people trying to do that. Okay, to be honest with you, okay, for those difficult problems, okay, you really don't need to make it polynomial. As long as you can reduce it. For example, the best known algorithm is n times 2 to the power of n, right? If you can come up with like an algorithm that's 2 to the power of n, you can get rid of that n, just reduce the order a little bit. But still it's like a polynomial. Also, still as an exponential. It's just that you reduce the order a little bit. That's good enough. You become famous. You already become famous. There are so many smart people in the world. They are trying to design algorithms to fit, to just get a better, just